Okay, uh, let's get started. So I'm just going to go through the final question by question. If anyone who's here has any questions, um, just stop me and we can talk about it. Okay, so the final is structured, or this practice final is structured basically like the both of the exams that you've had previously. In the beginning, there's some useful numerical quantities, so you don't need to take any inverses or anything like that. There's no Excel you need to do on the exam. There's 15 questions. All of them are all multiple choice. Maybe the first thing that I'll say is, like I always do, I would just, my test taking tip would be go through all of these questions. Just read when you get the exam, read through all of the questions, and try and pick out ones that seem like they might be easy questions that you can kind of pick off immediately, so you can have most of the time for the exam on some of the questions that need some computation. So if I'm scanning through, um, if I see questions one and two, they don't seem like immediate necessarily answers to me off the top of my head. They might take a little bit of thought. On the other hand, question three, for instance, if I give you a table like this, which is just the output of some regression software, uh, things like regress question three, just asking, okay, I have a hypothesis test regarding one particular variable, and I'm just asking whether I can reject this hypothesis test at a certain significance level. You should think of these questions as very straightforward and quick. So questions like problem three, if I saw a question like this, I would mark this in my head and say, okay, this should take me 5 seconds, 10 seconds. This should be a quick question. Same thing, questions like four, what is the distribution of this test statistic? This is just, do I remember what this is or not? Do I remember what this p-value is actually corresponding to? So this is a question that either you know it and it'll take 5 or 10 seconds to just go through and get the answer, or you don't quite remember. If you don't quite remember, I would say this is something that if you don't remember it off the top of your head, um, you can probably recalculate it and try and understand it, but I would save then the question for last. So it's either the question you do first or the question you do last. I would then go through question five seems basically to fit the same bill as question three. So I would mark that as an easy one. We can get it done in 5 or 10 seconds. Question six is a little bit different. It seems like it should be a quick and straightforward one, but it's slightly different because it's got multiple hypotheses here baked into one. So this one I wouldn't mark as okay. Let's just do it in 5 or 10 seconds. Now we move on. Question seven, this seems like there's some calculation involved. Question eight, some calculation involved. Same thing with question nine. So I wouldn't go through and mark those as, okay, these are 5, 10 second questions. I'll go to question 10. Here, this true or false question regarding, again, testing at a significance level 0.05 about a relationship between two variables. This seems like it's pretty straightforward, so I might try and do this one immediately. Same thing with this question. This question also seems like there's not that much calculation that needs to be done. I then go through, we only have a few questions left. This question 12, this indicates some calculation. Same thing with question 13. But question 14 is just asking, okay, what is the distribution of this random variable? And I don't even need to specify exactly what it is, just what's the type of the distribution. So question 14 seems a bit straightforward to me. And question 15, there seems to be some calculation. So question 15, I wouldn't do immediately. Question 14, I would do immediately. And this way, in almost all of these kinds of chunks of questions, you've picked off at least one of the questions in there. And you've picked off basically a third of the exam by going through. So hopefully by that point, you've done that in the first maybe 5 minutes of the exam. And now we can go through and we can do everything a little bit more carefully. So you don't have to do it that way. That's just how I would do it if I were taking the exam. But now that we've done this, we've kind of familiarized ourselves with what's going to be on the exam. We can just go through. So this first question, indeed these first two questions, they concern the following problem. So we observe samples, y1 through in, and we're told that they come from this model, y is equal to some parameter theta plus some noise n. And the noise, we're given the distribution. It has this distribution e to the negative absolute value of x all over 1/2. Now, the question is, if we wanted to actually compute the maximum likelihood estimate in this model, which of the following loss functions would we try and minimize? So this problem is very similar to basically what we did in the notes, where we derived the maximum likelihood estimator for in the normal linear model. So let's just go through this. So I'll say that p theta of some observation, let's say p theta of y, this is equal to the distribution of y if the value of maybe let's call theta prime here of theta were theta prime. What the maximum likelihood estimator then wants us to do is we want to maximize the probability. So we want to maximize over theta prime the probability of seeing everything that we saw, which is y1 all the way to yn. Now, this quantity here, the probability under theta prime of y1 to yn, this is equal to the product from I equals 1 to n of the probability under theta prime of yi. This is because of independence. Now, each of these, we're actually given what this distribution is, right? We know the distribution of n. So the probability under theta prime of yi is equal to the probability under n of yi minus theta prime, just by subtracting theta from both of these sides. So that means that this quantity here is Pn of yi minus theta prime. We know what Pn is, so this is equal to the product from I equals 1 to n of 1/2 times the exponent, e to the power absolute value of yi minus theta prime. Okay, now we're almost done. We want to remember, maximize this expression in theta prime. In order to maximize this expression in theta prime, it's equivalent to maximize the log. This is because the logarithm is an increasing function. And let me be clear, this is the natural log, which is equal to a constant plus the sum I equals 1 to n of the natural log of e to the negative yi minus theta prime, which is equal to a constant minus the sum from I equals 1 to n, the absolute value of yi minus theta prime. Now, what is this constant? This comes from when I take the log of this product, this is going to turn into the sum of the logs of each of these terms. But the log of this term is the log of 1/2 plus the log of this exponential. And the log of the 1/2, this is just a constant. It doesn't matter what I take theta prime to be, that 1/2 is not going to change. So we'll just group all of those into this constant here. The only term that really matters for us is this quantity here. And now we're basically done. We want to maximize this expression in theta prime. This is equivalent to minimizing 1 over n, sum from I equals 1 to n yi minus theta prime. So now if we go back to these answers here, that's exactly this quantity here. Okay. So this is the first question. We went through the gory details here. These details are exactly the same as is in the lecture note and what we did in class. So we basically repeated most of those details. One way you might be able to have guessed the answer, if I were looking at this, if I were taking the exam, I saw that the noise looked like this. Immediately from this, I would guess that there's going to be some absolute value in my answer. So my guess, just pattern matching, I would probably eliminate A and B in my head and think, okay, it's one of C and D. And now, because the way you might have guessed C before doing all of this, of course, you should do this to make sure that you get the right answer. But if you're under a time constraint, C seems the most reasonable just a priori even before doing these calculations, because we knew that in the lecture note when we did these calculations, we were going to take a log somewhere. So we're not going to expect this actual exponential to pop out. The second thing is we wouldn't expect a sum and an exponential. So if we have a sum, we would expect whatever the argument of the exponent is. If we had a product, we might expect the exponential, but here we have a sum. Okay, so that's it for question one. And in case it's helpful, I mean, you already have the solution. In case it's helpful, I'll upload these handwritten notes as well after this session. So the second question is, now that we know which loss function we're actually minimizing, let's do it for a small problem. So here we're going to try and minimize this with y1 equals 1 and y2 equals 2. So we want theta which minimizes 1/2 y1 minus theta plus 1/2 y2 minus theta. We're given y1 and y2. So this is 1/2 times 1 minus theta, absolute value, plus 1/2 times 2 minus theta, the absolute value. And then we want to minimize this quantity in theta. Now, we can do a little bit of kind of guess and check work just to narrow our range down a little bit. So let's call this f of theta. Note that f of 1, this is equal to 1/2 times 2 minus 1 equals 1/2. And the same thing, f of 2 is equal to 1/2. So we know that for any value theta, if we get a value of f for that corresponding theta, which is greater than 1/2, there's no way it can be the minimizer. So let's see something that happens if theta is greater than 2. Then we can look at this thing and we can say, okay, if theta is greater than 2, then 1/2, 1 minus theta, this is going to be greater than 1/2. And this term is always positive. So theta cannot be a minimizer. On the other hand, if theta is less than 1, then 1/2, 2 minus theta, is greater than 1/2. So theta cannot be a minimizer. Which means theta has to be between 1 and 2. Now the question is, what value is it between 1 and 2, or what values between 1 and 2 can theta take? So let's just look at this line here. So here's the value 1, here's the value 2. We know theta is somewhere between this. But this quantity here, this is the absolute value of 1 minus theta. And this quantity here, this is the absolute value of 2 minus theta. There's a question in the chat. Okay, so someone asked, where do you get the value 1/2? So there are a couple of places. So here, this value 1/2, this comes from this 1 over n, and then just plugging in n equals 2. The 1 over n, you don't really need it. It won't affect your answer. So if you see here, if I didn't have the 1 over n here, it would all be fine. So you don't need to carry around this 1/2 if you don't want to. It doesn't affect anything. It's scaling everything. But if we're using the loss function here, the 1/2 comes from this 1 over n, and n equals 2 in this case. And then in f of 1 and f of 2, I get this 1/2 right here and right here. This is just by plugging into f of theta. Theta equals 1 and theta equals 2, and evaluating the function. Hopefully that answered the question. If not, feel free to follow up. But so going through now, if I look at theta between 1 and 2, and I look at this sum of 1 minus theta absolute value plus 2 minus theta absolute value, it's always going to be equal to 1. So it doesn't matter where theta is, the sum of these two quantities is always equal to 1. That means that for theta between 1 and 2, the value is always equal to 1/2, which means that the answer is D. All of these values have the same quantity, and they're all minimizers. So that's the entirety of the first two problems. These are related to maximum likelihood estimation, doing loss minimization, understanding what it means to fit a model. Here we fit the model, where the model we're actually trying to fit is what this value of theta is. It's a very simple model. It's a constant model, but we're still model fitting. Okay, so we can move on now to the second question. Okay, before that, cool. Okay, so we can move on to this second set of questions. So the second set of questions are now related to the output of some regression study. So here the setup is the following. We're studying for an exam. Some article claims that the time you spend studying for exam and also the amount of basketball that you play the week before the exam are significant linear predictors at the level alpha equals 0.05 of your exam score. So you dig in a little bit and you see that the author of this article collected data, yi is your exam score, x study I, this is how many hours did you study, and x basketball I, so how many hours did you play basketball, and they try and fit a regression model of the following. So y is the exam score, beta 0 is an intercept, beta study is the coefficient corresponding to how many hours you study, and beta basketball is the coefficient corresponding to how many hours you play basketball. Now, given this data, the authors ran a regression model, let's say in Excel, and one subset of the output of the regression was the following. So for the variable study, the coefficient was 2, the p-value was 0.01. For the variable basketball, the coefficient was 5, and the p-value was 0.045. Now, the first question is really what we want to see is we want to understand, is the amount of time that you spend studying, is this a significant predictor of your exam score? So in order to do this, you set up the hypothesis test. The null hypothesis is that beta study, so the coefficient corresponding to this quantity x study, is equal to 0. That means that if this is equal to 0, the amount of hours you study has no linear relationship at all with your exam score. The alternative hypothesis is that there's something interesting. So the amount that you study does have a linear relationship with your exam score. So the question here now is, from the output of this regression, can you answer the question? There is now enough evidence to reject the null hypothesis at significance level alpha equals 0.05. Now, the point of this question is that these p-values are exactly corresponding to this hypothesis test. So remember, in order to reject this null hypothesis at significance level alpha equals 0.05, we want a test which does the following. So this is our type 1 error. We want to control our type 1 error at level alpha, which is 0.05. The canonical test that we use is reject H naught if the p-value is less than or equal to alpha. So in these kinds of cases, because this p-value is exactly the p-value corresponding to this hypothesis test, we can just look at the table. We can check, okay, is this p-value less than our significance level? The p-value is 0.01. Our significance level is 0.05. 0.01 is less than 0.05, so we can reject the null hypothesis. Okay. Now, the next question, this is just a I wouldn't say necessarily conceptual question. It's mostly asking, do you know what this p-value means and what it corresponds to? So this question, the answer to this, can be found in the linear regression exercises in question 3, where the point is really there that we see that beta hat 1, when sigma hat is unknown, is t-distributed. And in order to actually do this hypothesis test, you're using a test statistic, which is based on this quantity beta hat 1, your fitted coefficient, or rather beta hat study. So this test statistic is actually based on the t-distribution. Okay. So next problem is very similar to problem 3. We're considering testing the hypothesis where the null is that beta basketball equals zero. So the null hypothesis that there's no linear relationship between the amount of hours that you play basketball and the score that you get on the exam. And the question is, can we reject the null hypothesis at significance level 0.05? This is the same game. We just check the p-value. If it's less than significance level, we can reject. So in this case, point p-value equals 0.045, which is less than 0.5, 0.05, so we can reject. And the answer is true. Okay, so going through these, this seems to suggest that if we look at beta study in isolation, there is a linear relationship, or there does appear to be a linear relationship between the amount of hours that you study and the exam score. There also appears to be, in isolation, a linear relationship between the amount of hours you play basketball and your exam score. Okay, so let's go to question 6. Question 6 is slightly more complicated in that here we have two hypotheses. So here in our null hypothesis, we're asking, is it true that both beta basketball equals zero and beta study equals zero? So this null hypothesis is slightly stronger. It says that there's no linear relationship between the amount of hours you play basketball and the amount of hours that you study. Neither of these variables has any bearing at all on the outcome. Now, this question, this is an instance of what's called a multiple testing problem, where the issue is that if I try and test many, many variables, say hundreds or thousands of variables, and I'm interested in significance level alpha equals 0.05, if I try to just reject the null hypothesis at that level for each of these variables individually, which is what the output of this software gives me, I'll get a bunch of what are called false discoveries. So I'll falsely reject some null hypotheses which are actually true. So this is the thing you have to be slightly careful of in these kinds of multiple hypothesis testing problems. So what do we want to do here? We're still trying to control the same game. So we still want to control our type 1 error. So we still want the probability of H naught, of rejecting H naught to be less than or equal to alpha. Now, in question 5 and in question 3, the test that we used to reject H naught was clear. We just checked, okay, is the p-value less than alpha? If it is, reject. If it's not, fail to reject. Here, because we have two variables and there's only individual p-values corresponding to each of these variables, but nothing about both of them combined, we can't necessarily just do that. But we can consider the following test. We can reject H naught if p-value basketball is less than or equal to alpha over 2, or p-value study is less than or equal to alpha over 2. So now the questions, what we've done is we've reduced the significance level of each of these to something much smaller, alpha over 2, and now our testing procedure is going to reject if either of these things holds. Now, this gives type 1 error control. Why does it give type 1 error control? So let's go over here. This is because now this probability is equal to the probability that you reject H naught basketball or reject H naught study, which is by the union bound less than or equal to the probability that you reject H naught basketball plus the probability that you reject H naught study, which is alpha over 2 plus alpha over 2 equals alpha. Okay, so whatever testing procedure we just defined, in particular this testing procedure here, this now has type 1 error control at the right level, alpha equals 0.05. So now all we have to do is we have to check if either of these p-values is less than or equal to alpha over 2, which is 0.025. So if we go here, we check, okay, is the p-value corresponding to basketball less than 0.025? No. So we check is the p-value study less than 0.025? This p-value is sufficiently small. It is less than 0.025, so we can actually reject. So this is the answer to this question. Someone asked in the yes, the a multiple it does the output of this software always does use the t-distribution. Unless you are specified otherwise, the default is to use the t-distribution.
So for question 6, do we just divide alpha by 2 and then compare the p-values?
Divide alpha by however many are in here. So if I give you like 5, if there were 5 variables in the study and your null hypothesis was that all 5 of those variables are equal to 0, then you divide alpha by 5.
Okay, thank you.
So this is known as a Bonferroni correction. Yeah, an aside that doesn't matter for the exam is that these multiple testing problems, like in problem 6, these are things that have been pretty active area of research in statistics in doing better multiple testing procedures that waste as little data as possible over the last, say, 10 or 20 years. Anyway, so we'll move on to the next question. So the next set of questions concern the usual normal linear model. So we observe a sample of size n, where our responses are yi, our variable is xi, and each of these come from the normal linear model where y is some coefficient beta 0 star, this is the intercept term, plus a coefficient beta 1 star times x, our variable, and this is corrupted by some noise, sigma g, where g is a Gaussian, and the standard deviation of the noise is sigma. Okay, so the first question is we're told that we make 50 observations. We're told that the standard deviation is equal to sigma is equal to 1. And we have a fixed design. So the values of x that we actually look at here are xi is equal to I. Now, the question asks, if we run our regression software and we see that beta hat 1, so the fitted value of this coefficient is equal to 2, and this is the fitted value by minimizing the linear least squares loss, our goal is to find a 95% confidence interval for the true coefficient beta 1 star. Okay, so the key distribution here is that if sigma is known, then we have beta hat 1 minus beta 1 star is equal to sigma over the square root of n times the empirical variance of x times a standard Gaussian. So in particular, this means that beta hat 1 is normally distributed if we know sigma. And once we have this, we can immediately write down the confidence interval, Cn is equal to beta hat 1 plus or minus phi inverse of 1 minus alpha over 2. Make this clear that this is a plus or minus, times the standard error, which is sigma over root n times the empirical variance of x. Okay, now if we go through what we're given, we're given that beta hat 1 is equal to 2, so we know this quantity. We're given that sigma is equal to 1, so we know this quantity. We know n, it's 50. And we know alpha, so we know alpha is 0.05, 1 minus 0.95. So here, we also know this quantity. This quantity is phi inverse of 1 minus alpha over 2, which is phi inverse of 1 minus 0.05 over 2 equals phi inverse of 0.975. And if we go and look in what we're given, that should be there. It's exactly right here. It's 1.96. So this is 1.96. So we know all of these quantities except for this empirical variance. So now we just have to plug in and figure out what this empirical variance is. Uh, so in order to do that, I'm going to zoom in here. The empirical variance is equal, by definition, to this quantity. Okay. Now we know what our design points xi are. So we know that each xi is equal to I. So this is equal to 1 over n, sum from I equals 1 to n of I squared minus 1 over n, sum from I equals 1 to n of I whole squared. And now the hint tells us exactly what these sums are. So this first one is given here. This is 1 over n times n plus 1 times 2n plus 1 over 6 minus 1 over n times n plus 1 over 2 squared. Now we know what n is. This is 1 over 50 times 50 times 51 times 101 over 6 minus 1 over 50 times 50 times 51 over 2, whole thing squared. And now this is something we can plug into our calculators. This is equal to 208.25. So we can plug in that value here. And if we plug in all of these values together, what we'll end up getting is this quantity here, C. There's another slight trick in these answers if you want to just immediately eliminate things, which is that if you know, once you know in the beginning that sigma is known, and so you're going to have this kind of confidence interval. So your confidence interval looks exactly like this. You can immediately rule out these two options because you know that your confidence interval is going to be centered at beta hat 1 equals 2. So the only two options that make any sense are C and D. These two just you can immediately roll out before you do any of the calculations. Just check if there's anything in the chat. Cool. Okay, so let's move on to question 8. So maybe just before I do this, questions 7, 8, 9 are really just calculating confidence intervals for various quantities that we deal with in these regression studies. 7 is if you have oracle null. So if someone does something in the chat. How would we solve if sigma is unknown? We'll do that in question 9. So we'll see what we do in question 9. It's a great question. Question 7 is if sigma is known, what do you do? Question 9 is if sigma is unknown and you have to estimate sigma, what do you do? And question 8 is somewhere kind of in between. It's not about beta hat 1, it's about actually sigma. How do we estimate sigma? And can we do some uncertainty quantification for sigma? And so in particular, just so you have a place to look, I would look for question 7 in the linear regression inference node. And questions 8 and 9, 8 is question 1 in exercises. Is this what the node is called? Yeah, exercises linear regression. And 9 is Q2 in the same thing. So questions 8 and 9, we already did them in general. They're the exact same questions as question 1 and question 2, just with the specific numbers plugged in. Okay. Oops. Cool. Okay, so let's actually do this in question 8. So we know actually from this node, from this question, that sigma hat squared over sigma squared. This is distributed as a chi-squared random variable with n minus 2 degrees of freedom over n minus 2. And we're going to use this to construct a confidence interval. So the only thing we need to do here, the only randomness in this confidence interval is going to come from this chi-squared n minus 2 random variable. So we need to trap 95% of the mass of this chi-squared n minus 2 random variable. In order to do that, we want L such that the probability that a chi-squared with 48 degrees of freedom is less than or equal to L is equal to alpha over 2, and R such that a chi-squared with 48 degrees of freedom less than or equal to R is equal to 1 minus alpha over 2. Now, why 48? This comes from the fact that we have n equals 50 observations. And here, the distribution that we're interested in is the chi-squared with n minus 2 degrees of freedom. So n minus 2 here is 48. Now, these two quantities we can just get by inverting the chi-squared distribution. So here, L, I'm going to give myself a little bit more space. So L is equal to the CDF of the chi-squared with 48 degrees of freedom, inverse of alpha over 2. We know what alpha is. So this is F inverse chi-squared 48 of alpha is 0.05. So this is 0.025. And this quantity, if we go all the way up here, this is given right. I see. This should be here. There's a typo in this. This should say chi-squared 48. And this is given here. Someone asked this on Brightspace discussion, and I didn't catch this. This is indeed with 48 degrees of freedom. So this quantity is 30.75. We can do the same thing for R, which is F inverse chi-squared 48 of 1 minus alpha over 2, which is equal to F inverse of chi-squared 48 of 0.975. And again, we can go here. This time it's actually there, 69.02. And now our overall confidence interval is equal to sigma hat squared times. So all we're going to do is we're going to take this thing, we're going to multiply n minus 2 on both sides, divide by chi-squared n minus 2 on both sides, and multiply by sigma squared on both sides. So that means that sigma squared is going to be trapped between sigma hat squared times n minus 2 over r, and sigma hat squared times n minus 2 over L. We substitute n minus 2, this is 48. R is equal to this quantity 69.02. L is equal to 30.75. And sigma hat squared is 2.5. When we plug each of these quantities in, we end up getting C. Just check the chat one time. Cool. And that's the answer for question 8. Okay. Now, question 9 is the same drill as question 7, except here, the key for Q9 is beta hat 1 is t distributed. So if you plug in an estimate of sigma hat and you don't use the true value of sigma hat, now the coefficient beta hat, this follows a t distribution. And in particular, if we use question 2 in these exercises sheet, so we use the confidence interval that's given here, our confidence interval is equal to beta hat 1 plus or minus ftn inverse of 1 minus alpha over 2 times sigma hat over the square root of n variance n of x. And now we're done, basically. Beta hat 1, we know it's 2. We were given that here. Sigma hat, we know It's the same quantity here. So we just need to take the square root of this. Alpha we know, alpha is 0.05. So we just need to plug in ft inverse n minus 2 of 1 minus alpha over 2. So this is ft inverse at 48 degrees of freedom, evaluated at 0.975. So that quantity is exactly right here. That's 2.01. So let's write these all down. This is equal to 2 plus or minus 2.01 times sigma hat, that's the square root of this, of square root of 2.5. And the square root of 2.5 is what? It's 1.58. In the denominator, we have an n, which is 50. And then we have the empirical variance, which we already computed, is 208.25. So now that we have each of these things, we can plug this into our calculator. Again, we can take away these last two answers. We know they're not going to be correct because they're centered at the wrong value. And plugging everything in, we get this. 2 plus or minus 0.031. Okay. So that's it for this block of questions. Now, again, this block of questions, there was some calculation we needed to do, but this calculation is fairly formulaic. So each of these questions, 7, 8, and 9, there's a formula that you can just plug into. For 9, it's this formula. For 8, it's this formula. And for 7, it's this formula. And as long as we know how to plug into these formulas and we can calculate the various quantities, this is something we should be able to do. Okay.
So, like for question 9, if we're
Mhm.
given sigma hat squared,
Mhm.
we just take the square root of that to get sigma hat
Yes.
and
Yeah.
use that. Okay. Okay.
So someone asked in the chat also, it's a great question for question 8. Are we supposed to use R in the denominator here or L in the denominator? We are supposed to use R in the denominator here because in these so this is the variance confidence interval is interesting when we compare to the coefficient confidence interval because usually here we're centering at something and then we're adding plus or minus, whereas for the variance it's actually multiplicative. And because we have things multiplicative, when we invert these things, so we've trapped chi-squared between two values. So on the lower end, it's less than or equal to L. On the upper end, it's less than or equal to R. But when we then want to invert this into a confidence interval, we're going to end up getting this chi-squared guy. This is going to be in the denominator here. So because it's in the denominator here, the larger it is, the smaller this value gets. So that's why we want the R on the left end point of the confidence interval. So it's the right point for the actual random variable, but it'll be the left in our confidence interval in the denominator. Okay, cool. So let's move on to the next block of questions. So this is about some physical law, which we don't have to know anything about. So the question is the following. There's some physical law, Coulomb's law, which states that the electrostatic force between two charges is given by the function F equals K times Q1, Q2 over R squared. Now, you see this and you want to put this theory to the test. So you go to your lab and you collect samples, RI, where you take the charges and you move them at different distances from each other, and you record at each distance RI what is the electrostatic force that is between the two charges. So now you've varied this a bunch of times, and now you say, okay, let me fit a linear regression model where I run a regression of this force on the actual distance Ri, and I obtain the following results, where I see here the variable R distance, I get some coefficient 10 to the 10 to the eighth, and the p-value is 0.5. So the first question is, true or false, this data, and in particular the outcome of this regression, suggests that at significance level 0.05, there is absolutely no relationship between R and F. So the answer to this is false. So it does suggest that there is no particular kind of relationship between R and F, In particular, it suggests that there is no linear relationship between R and F. So this regression output suggests that F is not equal to some constant C multiplied by R. That's all that this data tells us. So this is important when we run our regression software and we get these p-values and we make these significance claims. Having a large p-value doesn't necessarily rule out the fact that there's any relationship between these variables. It's just suggesting that there's no linear relationship. We're only fitting lines to these things. So the next question is that you decide to run your regression a little bit more carefully and you transform your variable. So instead of running a regression on Ri, you run it on 1 over Ri squared, which is what you think the relationship should actually appear like in the theory. And now when you run your regression, the output of the software is the following. You get a much smaller p-value and you get a different coefficient. So now this is asking, what does this suggest at significance level 0.05? And before we read these, what we can read off from this suggests that there is a linear relationship between this quantity, 1 over Ri squared, and Fi. There's a linear relationship between these two. So this suggests that F is roughly equal to some constant. What is this constant? It's 8.9 times 10 to the 9th times 1 over R squared. And so in particular, what it suggests is that there appears to be a linear relationship between 1 over R squared and this electrostatic force. Okay, so that's it for this block of questions. Let's go on to the next block.
Wait, Professor, I'm
Yes.
confused about how you know that there's a linear relationship.
So it suggests that there's a linear relationship. So there appears to be a linear relationship here. Because here, when you run this regression, what is this p-value corresponding? It's corresponding to, okay, so let's go back 1 minute. So in question 10, here you're trying to fit this kind of model. F equals beta 1 times R. This is the model that you're trying to fit. And you're trying to test the hypothesis beta 1 equals 0 versus beta 1 not equal 0. Now, this p-value says we can't necessarily reject this null hypothesis, so we don't really know if there should be a linear relationship or not. In question 11, now you're trying to fit a model of the form beta 1 times 1 over R squared, because here you've transformed your variable from R to 1 over R squared. And now you're trying to test the same thing here. But here, because the p-value is very small, it's less than the significance level, which is 0.05, you can actually reject the null hypothesis, which seems to suggest that there is a non-zero coefficient beta 1 that actually fits this model, which means that there's a linear relationship because there's this coefficient here, which is not 0, between this quantity and this quantity. Does
Okay.
that clarify it?
Yeah, thank you.
Okay. Okay. So let's move on now to the next block of questions. So the next two questions are about a very simple model of classification. So in these questions, we have observations from this model here, where we observe X, and at least in the quote unquote training set, we'll observe values of X and Y. And what we would actually be interested in doing is given a value of X, predicting what the value of Y is. Here, we're not going to actually do any prediction. We're just going to try and fit these models to data. So what is this model doing? It's saying that y is going to take two values. It'll take either the value 1 if this quantity is greater than 0 or greater than or equal to 0, and y will take the value -1 if this quantity is less than 0. Now, the model is that this random sign, y, is equal to the sign of some fixed thing, beta 1 star times x, plus some noise u, which is uniformly distributed between -1 and 1. So question 12 is asking if we see one observation where x1 is equal to 5 and y1 is equal to 1, which of the following values describes the maximum likelihood estimator of this coefficient beta 1 star? So what do we want to do for maximum likelihood estimation? We want to maximize in beta 1 the probability that y1 is equal to 1 given x1 is equal to 5. So we want to maximize the probability of seeing this observation. So we want a beta 1 that maximizes this probability. What is this probability? This is equal to the probability if we just plug in our model that sine of beta 1 times 5 plus a uniform um, is equal to 1. Now, if the sine of this value is equal to 1, that means that this quantity is greater than or equal to 0. So this is equal to the probability that beta 1 times 5 plus u is greater than or equal to 0, which is the probability that u is greater than or equal to negative beta 1 times 5. Now, this is just a question about this uniform random variable u, and we need to find a value of beta 1, which makes this probability as big as it possibly can be. Now, the point is, if I take beta 1 greater than or equal to 1/5, then negative beta 1 times 5 is less than or equal to -1. What that means is that for any value of beta 1 greater than or equal to 1/5, this quantity is always less than or equal to -1. Now we know that this random variable u is uniform between -1 and 1. That means that this random variable is always greater than or equal to -1. So that means that in this case, is equal to 1 if beta 1 is greater than or equal to 1/5, and that's B. Okay. All right, we can move on now to question 13, which now, instead of taking into account what this actual model is, we can just pretend that we don't actually know what the model is, and we can try and just misspecify and fit a line, y equals beta 1 times x. Now, if we try and do this, we might try and minimize the squared error. So here, want beta 1, which minimizes y minus beta 1x squared. We know what y is. So this is 1 minus beta 1. We know what x is. It's 5 squared. So we take beta hat 1. The minimizer of this is just 1/5, which is this quantity here. So in this special case, despite the fact that we threw away there is absolutely no reason this should be a good model, but for some reason, despite the fact that we're just fitting a linear model to something totally nonlinear, we still end up getting a maximum likelihood estimate. This won't happen in general, but this is just some luck of this particular model. Okay, so that's the entirety of these two questions. Let's move on to the last two. In the last two questions, these are related to a transformation of your variables. So here we're told that the data actually comes, the responses are a linear model, so beta 1 star times x plus some Gaussian noise raised to the third power. Now the question 14 is, which of the following describes the distribution of this conditional quantity, y to the 1/3? So if I take 1/3 power on both sides, given x. Now this one, like I said in the beginning, this we can just look straightforwardly and see, okay, what happens if I take both sides to the 1/3? I get 1/3 is equal to beta 1 star x plus sigma g. This is fixed. This is the random quantity, and this is Gaussian. So the distribution is Gaussian. And that's the entirety of the question. The next question is now in this transformed model, we want to actually fit these coefficients beta 1. And suppose that we do that, since we know that y to the 1/3 follows a linear model, we can just try and fit the linear least squares to that. If we have only one observation, we're told that this noise standard deviation sigma is equal to 1, and we have just the variable x1 equals 1, and we try and fit beta hat 1 by minimizing the squared loss. Let's try and compute what is a 99% confidence interval. Here, this is also once you've noticed in question 14 that this quantity is Gaussian, this is now fairly straightforward. So beta hat 1, this is equal to, we fit this model. So this is equal to y to the 1/3 over x. We're told that x1 equals 1. So this is just y1 to the 1/3. And now we know y to the 1/3 is equal to beta 1 star times x plus sigma g. So this is equal to beta 1 star plus sigma times g. Sigma is 1, so it's just a Gaussian. So that means that our confidence interval here with just one observation is um, Ci centered at beta hat 1 plus or minus V inverse of 1 minus alpha over 2, which is equal to beta hat 1 plus or minus V inverse of 1 minus 0.01 over 2 equals beta hat 1 plus or minus 2.58, where we get this from this quantity right here. And that's, oops, B. Okay, so that's the entirety of the practice exam. Let me stop the recording now.